Welcome everyone. Welcome to this Qualcomm lecture series. This is under the auspices of National Supercomputing Mission Nodal Center for HPC and AI. Um, and this lecture series is about various aspects related to, let's say, a combination of compilers and machine learning. When Arun mailed me about this set of lectures, I was very happy to know that these lectures are quite pertinent from the perspective of not only, let's say, Qualcomm or in particular industry, but these are kind of nowadays foundational that are required in many industries. And therefore, we thought that we should have this for all, not only IIT Madras students, but even people all over India. And I see that the number of attendees is increasing. When I thought about inaugurating the session, I felt that I'm not the most suitable person to inaugurate it. I mean, although I'm a teacher, sometimes teaching the kids itself becomes very difficult for me. And then making the machines learn on top of that is doubly difficult for me. But there is a good colleague of mine, Dr. Pratyush, who manages both these things, I mean, making the kids learn as well as the machines learn. Pratyush has done his PhD from ETH Zurich, and he has interests in deep learning, cyber physical systems, etc. He teaches courses related to operating systems as well as GPU programming, systems engineering in deep learning, etc. And he is probably the right person to inaugurate this session. So I welcome Pratyush. Pratyush, go ahead.
Yeah, thanks, Rupesh. So I think the way it works with teaching students and machines is you teach the students and then they figure out clever ways to teach the machine. Right? So I think that's what is working out. But I would like to first begin by thanking Rupesh for all the effort around the National Supercomputing Mission. I think it's a great initiative. He has been working with multiple IITs, with CDAC, with the government of India. I think the service to the department, to the institute, to the country, I think that's quite reflective. So thanks, Rupesh, for that. Now, with for the topic at hand, compilers and machine learning, high-performance computing, I think we all recognize that compilers are a central piece in computer science, right? In translating the intention of the programmer into what actually executes on hardware. And I think it's always considered a core thing that we need to get right when we build computing systems. But I would say perhaps 10, 15 years back, it looked like compilers are a niche topic, right? You need to design a few programming languages and build compilers for them. So it became a smaller community. And I see that changing now for two particular reasons, at least the way I understand it. One is that, interestingly, with all this machine learning and deep learning, different people. So, for example, there is a game developer, or there could be a scientist understanding protein folding, or there could be a climate modeler. All of them are starting to use the same tools, right? It could be deep learning, or it could be at least some abstract form of deep learning, right? So this coming together of a variety of computational methods onto the same tool flow, that is creating a lot of let's say, focus on improving the middleware, the tool chain itself, right? So that's one trend. And the other trend is also something that you might have seen, which is multiple companies are now building hardware, right? Again, what looked like the niche effort of some companies building hardware for 30 years now is open to many, many startups. In fact, more than 100 startups have their own accelerators for machine learning. Most of the big tech companies are now outdoing the old companies. I shouldn't be saying that. Qualcomm is still holding fort, at least in the mobile space. But it looks like designing hardware is not as difficult as it used to be, right? Which also means that you need more complex tool chains, in particular compilers, to be able to target this wide diversity there is in hardware. And so I think we are in this phase where, at least in the evolutionary language, they say Cambrian stage of evolution, where there are lots of options. Many may die out in the coming years, but at least for now to the next 5-6 years, I see that a lot of work will happen on trying out different ideas and see which ones actually survive. So I think we are in a golden period for at least compilers, middleware, hardware design, and so on, driven by this focus on deep learning. So in this context, I find these lecture series very relevant, and also it's good that we have a large attendance. So again, thanks to Rupesh for that. So with that, I would give it back to Rupesh and actually let him officially inaugurate the series. Thank you.
Thanks, Pratyush, a lot. So Sushim, you want to say something?
Sure. So we have Amiya here, and we are, it's ironic. We are at the National Supercomputing Mission, and I'll talk about a very different thing about him. So when this whole smartphone, Amiya is our Vice President Engineering. We all report to him. Not only the compiler design, but some part of software security, machine learning, power system, architecture stability, stability test, CI/CD, and a lot of full stack teams report to him. But that's not about him. So Amiya, when this all smartphone thing came in, and they were all at high end one, the iPhones and the very expensive ones. So there was a concept talked about what the developing nations will do, or will there be ever a value tier, or will there be constrained CPU which can run a smartphone? So Amiya was the first lead of a value tier smartphone in Qualcomm and made it to the successful commercialization. And from there on, he has grown to lead all the Snapdragon 200, 400, 600, 700 chipsets. All of those chipsets are led by all of those leads of those chipsets report to Amiya. So all these chipsets program, Amiya is the global lead, and he has been a incredible pillar for the Qualcomm's value tier / high tier success. So over to you, Amiya.
Thank you, Sushim. Thank you, Rupesh sir. Thank you, Pratyush. Really appreciate giving Qualcomm a chance to participate in this forum, in this event. We are absolutely privileged and honored to be part of this forum and share some of the learnings that we've been spearheading within the company. Sushim and Ravi will talk about, both of you hit the right note about the challenges with education and machine learning and stuff. One of the challenges that we've been trying to deal with is how to make general purpose software run more efficiently, both in terms of performance as well as low power compute on our platforms. And hardware is just one part of it. You can design the hardware circuitry to enable accelerate the compute, whether it's neural compute, vector compute, or any kind of a multimedia processing. But you also need efficient software, and more importantly, the middleware that Pratyush spoke about, the tool chain that is needed to be able to make the same general purpose software run more efficiently, utilize the hardware acceleration that exists on a given platform. So some of the work that we are going to talk about, Sushim, Ravi, and the team are going to talk about, is centered around it. A lot of the core research around that work is happening in the Qualcomm India offices. Sushim leads that effort together with Ravi, who is directly the technology lead for that area. So we'll talk about TVM, which is essentially a compiler for machine learning. Compiler itself is a very niche area, and then machine learning is another niche area. And we've tried to join the two together and have compilers that are optimized for neural compute. We'll also talk about Halide, another area where Qualcomm has been spearheading a lot of work and on how to make image processing more efficient, the compute of image processing more efficient on the mobile platforms. And then, of course, there are other topics also that Sushim and Ravi are going to take care of. These are two very close to my heart, close to what Qualcomm does. A lot of work for these two areas have been done by the Qualcomm India team, helping evangelize both the technologies across all the portfolios or the mobile platform, the Snapdragon mobile platform that we are responsible for. So happy again to be part of this forum. My best wishes to all of you for success, for a successful event. And I really hope that some of the sessions that Ravi, Sushim, and the team are going to walk you through are useful, helpful, and help in both the efficiency and productivity of engineers. Good luck and all the best. Over to you.
Yep. Yeah, Ravi, thank you, Amiya. Ravi, we can get started. Just one quick thing for the participants. We have kept the sessions on a two levels. Like for TVM and Halide, we will go through an introduction, which is suitable for everyone. There will be two topics where we'll be deep diving, like the superblock scheduling and the neural inferencing. Then we'll come back to, again, overview topics on the program analysis and scientific writing and research methods. So you can choose and come on the topics as you wish and as you like them.
Sure.
Okay,
Thanks, Sushim. Yeah. Thanks, Sushim and Amiya. I request Ravi to start sharing his screen. And by the time that happens, let me give a quick introduction to Ravi. Ravi is in Qualcomm since 16 years now, and he has been working on various development tools like compilers, linkers, loaders, simulators, debuggers, and various IDEs. He is going to talk to us about Apache TVM, which is a framework for AI ML applications. Over to you, Ravi.
Right. Okay. Thanks, Rupesh. Are you able to see my screen?
Yes, the
Yes.
screen is visible.
Okay. Um, yeah. Thanks, Rupesh, for the invitation and for the introduction. And thanks, Ashna, for setting this up. I'm very happy to be here presenting about some of the work that we are doing. So. I don't have a lot of slides for today's presentation. This is going to cover the basic introductory part of TVM. Um, I hope I am audible, right? Please let me know if you are not able to hear me at any point of time.
So your voice is clear, no problem.
Okay. So this is the agenda today. I will. Sorry, someone said that I'm not audible.
You're audible to me, Ravi. Anyone, Ravi, is not audible? It's okay, Ravi. Go ahead. So while Ravi starts, that's the irony. We are at National Supercomputing Mission, and we'll be talking a lot about constrained programming and the constrained CPUs, contradictory to the supercomputer. So on this TVM front, like there can be two things which people can look at it. One thing is like people can use TVM. Those who are machine learning engineers, they need not worry about, as Dr. Pratyush said, need not worry about the underlying architecture, and the compiler will optimize it for you. And the same code can be portable across different platforms. While those who are from the systems engineering background, they can look at TVM as like the compiler team, what the magic they are doing. Like you write unoptimized Python code at the top, and they generate optimized machine code for whether it is a hexagon, Qualcomm hexagon running below, or x86, or NVIDIA, or a Samsung DSP, or a CY DSP. So that's the beauty of like the systems engineers who are creating this magic. Like you don't need to worry about the architecture. And the second thing which about TVM I would like to start is like since last 20 years I was seeing we'll put a good hardware block. The hardware guys will put a good hardware block, a good architecture, good ISA, but its programmability will be so tough that it will take a while for it to catch up. So that was another need of an interface like TVM or a Halide, that every engineer can program. The need to know the underlying architecture is not paramount. So that's the purpose of this talk. We'll keep it at the surface level. Those who want to deep dive, they can join later sessions which we do within the Qualcomm. We kept it for like no prerequisite kind of session today. Thank you.
Okay. Yeah, thanks, Hisham. Yeah, that summarizes pretty much the agenda that I have. I'll briefly talk about TVM, the philosophy, and how it makes it easier to develop the AI applications. And I'll talk about some debugging techniques, and then we can have a Q&A session and discuss anything that you would like to discuss. Before I start going into any details related to TVM, I'll take just a few minutes to give some idea about certain topics for the benefit of everyone who are not familiar with them. So I just want to make sure that everyone has at least some amount of familiarity when I start using certain terms. So our team is called LLVM team. And for the folks who are not aware of LLVM, it is an open source compiler framework started as a university project. but become very popular because of, for us, it's easier licensing terms compared to the other open source compiler, which is GCC. And also LLVM has modular design, which makes it easier to extend or to be reused based on any of the specific needs. In Qualcomm, we use LLVM framework as the base to develop our compilers and other tools for different architectures that we have. TVM is also based on LLVM infrastructure. So I'll keep using LLVM in my slides. I just want to make sure that everyone understands what LLVM is. The other thing is, I hope most of you are familiar with what Qualcomm does. Qualcomm's main products are chipsets that go into the embedded systems, like mobile phones. So in this context, the AI applications that I talk about are related to inference, not training. My talk is going to be focusing on executing a trained model on an embedded system. On embedded systems, they come with different sets of challenges compared to executing something on PC, right? The main thing is, apart from performance, the embedded systems are limited in memory. And the other important thing is, like, they have to be very power efficient. So this brings me to the next topic, which I'll touch upon, which is the Hexagon processor. Hexagon is a Qualcomm proprietary digital signal processor, which is very power efficient. Though it is Qualcomm proprietary architecture, everything is open. So you have the architecture, the tool set, the instruction set, everything available in Hexagon SDK, which you can download from Qualcomm's developer network website. I'll talk briefly about the architecture in the upcoming slides, but I think at this point of time, these things are sufficient for me to progress. As I said, I have very few slides, so I want this session to be as interactive as possible. Please feel free to ask questions whenever you want to. You can post them in the chat box. If I'm not able to see them or answer them, my colleagues here will be able to help me to stop and answer them.
Yeah, one thing is, like, TVM and Halide constructs are more or less similar. Since we were covering those constructs in the Halide session next week, so we kept it out of, like, for the sake of not having repetitivity, we kept it out of today's session. And today's session, you can more use it, like, ask me anything after, like, while we go ahead. You will have more chances to intervene us.
Right. Yeah. So I have very little text here, but I'll spend more time here. I'll have to switch between windows here just to show the TVM stack. Just like LLVM, TVM also was an academic project. It started as a research project in University of Washington. It is an end-to-end compiler stack which supports multiple targets as well as multiple machine learning frameworks. There is a wide industry adoption. A lot of companies, big tech companies, have invested in TVM, and they're using TVM in their products. So I just give some examples here. So let me just go back to the stack here. So can you see my screen? The TVM stack?
Yes.
Okay. The stack itself explains why we need a TVM. There are multiple reasons, but I want to highlight the important ones. See, if you see at the top of the stack here, there are multiple machine learning frameworks. Like there's PyTorch, there's TensorFlow, there is Keros, there is MXNet. Okay, and at the bottom of the stack, there are multiple hardware units, hardware blocks, not limited to only the ones that are shown here. As Prachis rightly mentioned, there are there are a lot of accelerators that are coming up, that have come up and that are coming up for the specific purpose of um, executing machine learning applications. Okay. So what happens with this is, and these are only two things, and also there are different kinds of models based on use cases. There are new models that are coming up every alternative day, just for taking care of new use cases. For example, the image processing is a completely different use case from like self-driving cars. Okay, so there are a lot of moving parts here. But just talked about this already. I just want to emphasize that a little bit. So we are at the period where there are a lot of things that are happening. There are a lot of changes at the higher top level where multiple frameworks are coming up, and there are a lot of changes here at the lower level where there are new hardware blocks are coming up. Okay, if you need to support this, this is a kind of Cartesian product of all sets. If you want to support a specific framework on a specific hardware, it's going to be completely impractical. Okay, if you think about it, this is very similar to the problem that the basic compiler design attempts to solve, which is dividing the compiler as front end and back end, right? So TVM attempts to solve the same problem. Okay, so at the top level, we have multiple frameworks, and TVM has an high-level IR. Sorry, does anyone have any question?
Ravi, there are a few in the chat box I answered. You can go ahead.
Okay. Yeah, thanks, Hashim. Okay. So there is a high-level IR here. The TVM calls it relay. So so there is a translation from the models that are written in these frameworks to relay, and also there are some graph level optimizations that can happen here, like quantization and everything. So the second layer, I'll talk about it. I'll come back to this again after I go through the other slides. There are the optimizations that happen at this level are operator level optimization. Okay, and there is something that's called auto TVM. I'll come back to this once I cover a few more slides. Then you'll have a better context to understand. And some of the optimizations that are related to operator at this level are like you can fuse the operators or optimize the graphs here, a certain part of the graphs. Okay. Then at the lower level, you can plug in any hardware that can use the IR from the top level. Okay. So that's for the TVM stack. Again, I'll come back to this once I cover a few more slides. Then I'll talk about it a little bit more. Okay. So the other thing is, as I said, like TVM can work at a little lower than just compiling the whole model. So you don't need to necessarily use TVM to compile the whole model, the whole network that gets generated by the framework that I showed. Okay, you can use TVM to compile individual ops also. Okay, the way that happens is like in the heterogeneous computing systems like Qualcomm. You may want to use one hardware block for specific computation and other hardware block for another kind of computation, or you may just want to balance or load balance the computation, right? let's say that you want to offload a certain part of your graph. I use graph model or network interchangeably. So you want to offload certain part of graph to DSP and a certain part to GPU. Okay, so what TVM can compile is TVM can do is like it can compile specific ops to DSP and some other ops to GPU. For example, you want to upload only ReLU operation to DSP. You can do that by using TVM framework. In most of my presentation, I'll talk about this programming model because this is what we are now using in Qualcomm, and the examples that I show are also related to this. I won't talk much about compiling the whole model, though it is possible in TVM. Okay, let's talk about simple programming model of TVM. So TVM programming makes it very easy for the developers to code and optimize their applications. Basically, the developers can use Python to write their custom operations. The basic programming model here is to separate out algorithm part from schedule part. Okay, this model is not new. This model has been taken from Halide, which is another domain-specific language widely used for image processing applications. We have a talk about this next week, which will provide more details. But the fundamental principle here is like the algorithm part is separated from schedule. I'll talk about what is algorithm and schedule when I go to the example, which will make it clear to you. Which should make it clear to you. Okay, and the next part that I'm going to talk briefly about is the Python operations that are written in Python. The TVM compiler, our TVM compiler helps to compile them for Hexagon DSP. Okay, so the DSP that I talk about has at a high level, it has two parts. One is the scalar part, which doesn't do any vector operations. And we also have a coprocessor called HVX, which is Hexagon Vector Extension, that does the vector or symbolic processing. Okay. So even though the whole model compilation is possible with TVM, which we aim to do eventually, right now we are trying to optimize the individual operations or the compilation of individual operations for Hexagon, so that it can be used in the existing workflow that we already have. Okay. The TVM for Hexagon, as I said, we have the TVM provides a Python interface. Users can write the operators in Python. I mean, I'm specifically talking about Hexagon, but it is true for any other.
Ravi, before starting the slide, there's a question in the chat box. How does TVM handle memory coherence and communication across the devices where the computation is distributed and scheduled? So I don't think we handle those kind of scenarios like distributed and scheduled. You have an answer to that, Ravi?
Right. Yeah. We don't do it by ourselves. I mean, TVM also doesn't do it by itself. We'll have to write an extra layer to handle those kind of situations. So basically, when you want to offload certain operations on one hardware block and other operations on other hardware block, then you'll have to have a control code somewhere that does this thing, right? Like that will have to handle this kind of scenarios when you want to do the concurrent execution.
Because in TVM, I don't think so. We have built anything like we have built in Halide, the .hexagon kind of directive, right?
No, we have that. We can offload the computation to one specific hardware block, but the
Not the
synchronization, not the synchronization between the blocks. So that has to be taken care of by the other control code.
I hope Aditya that answers your question. Go ahead, Ravi. He confirmed in the chat box.
Okay, yeah. As I said, you can write your operators in Python and compile for the hardware. Even writing the operators here, the operations, the code for the operators here is much simpler than traditional Python programming, especially for the folks like who are new to the hardware that they're programming to. So the other thing is like the code is portable. So once you write it, we'll make sure that it works even with the changed or upgraded hardware. The important point is, as I mentioned earlier, TVM borrows programming model from Halide, which is generally used for image processing.
Ravi, there is a question here, Ravi. What is an
Yeah.
operator? What is the word you are using? It is the data type?
No, it's the computation that happens. Like as I said, like average pooling is one operator, or convolution.
Or the one which we generally call in the short form ops.
Right. Yeah.
So that's a little bit of Qualcomm lingo. We use ops, so ops to operator. Yeah. Go ahead, Ravi.
Okay. So the programming model here is like separate program into algorithm and schedule. The algorithm is the part of the code which tells what is the operation that you are going to do, and schedule is the part that tells you like how the operation should be performed. So this kind of model, while it helps it to make it easy for the programmers to develop the code, it also makes it convenient for the compiler developers to generate the optimized code for specific hardware like HVX. So that brings me to HVX. HVX is part of Hexagon DSP subsystem, but it is a co-processor of Hexagon. It is the vector extension, which essentially means like it can do multiple operations, or it can operate on a large size of data in a SIMD kind of environment. Okay, so HVX can operate on data up to 2048 bits, which makes it very effective for the applications that operate on large sizes of data like image processing or deep learning applications. So TVM generates efficient code for HVX. So if you look at it, if you look at the instruction set or the architecture of HVX, it's not very easy to program by hand, which I mean either by assembly or the Hexagon intrinsics. So for a person who is very new to Hexagon or HVX, it's actually very challenging to write even the decently optimized code for their applications. So we have
that actually not only true for Hexagon. Any DSP, any proprietary DSP, like if you want to program in intrinsics or assembly, you have to understand the architecture and be the architecture expert from one DSP to another DSP or one chip to another chip. So probably like that's the point, Ravi, right?
That's right. Yeah, yeah, and also HVX has certain kind of instructions or certain kind of what I would call like the operations that would make it very difficult or very challenging to code by hand for someone who is not very familiar with the architecture. It's It's true with most of the architectures, but the thing here is uh, um, TVM actually um, abstracts everything, or hides everything from the uh, from the um, from the developers. Okay, so you don't need to learn. You will have to learn certain parts of the architecture, or certain details about the architecture to write your code in Python. But you don't need to learn everything related to the architecture to get best out of the hardware. So we have some benchmarks that we profiled against the hand coded assembly, and it is performing decently well compared to the hand coded assembly. Okay. And at this point of time, we have support for both simulator that is available as part of the SDK, and the hardware for TVM for Hexagon. Okay, that brings me to this slide, which actually drives the point that how easy it is to program using TVM. So the right side code is the assembly code, the Hexagon or HVX assembly code. You can see a lot of instructions starting with V, which is vector instructions. So if you see that for the same kind of operation, which is quantized addition, there is 601 lines of assembly code that needs to be written, and that's the optimized code for this operation. Okay, and compared to that, the TVM can do it in 25 lines.
I think I'll take that anticipated question already, like what about performance, right? That will be from the audience because we generally get it. So what happens is, like, what the time you save in productivity, two things. One, we do a lot of optimization at the back end. The second thing is, because your algorithm and schedule are different, and in this one, changing schedule in TVM, you can try it so fast, but you can try a lot of schedules in very short time. So for example, it is not exactly the TVM example. We were when initially Halide, when just us and Google were using it, and Google did for their Pixel 1 camera, the best camera ever, the ad. So they used Halide on that one, where their HDR plus pipeline power consumption went down by 50%. So sorry for the digression. So we had the similar question when everybody else thought it is still an academic project. So we were in China at a big place, and there were a big top VP sitting of multiple companies, and they said, "You are talking about productivity. Can you write a box blur in front of us?" So we wrote a box blur, and they had a hand optimized code. So hand optimized code was some 4 milliseconds or something like that. And when we did write the code, we write in few minutes for the box blur. We did wrote in few minutes. We first tried, it was 10 millisecond plus. And we second tried, it was again same region. We kept changing the schedule. And within 10 or 12 minutes, we could do 15, 20 plus retries. And all of a sudden, one change, we got in the range of their or below their handwritten assembly. So your productivity, your time to iterate becomes pretty easier. So Ravi will show the benchmarks. Right now, our TVM is in very initial stage as compared to Halide. In Halide, we already beat most of the hand assembly benchmarks. But in case of TVM also, we are coming pretty close by very frequently able to iterate the scheduling, or very quickly able to iterate the scheduling. And when the hardware version changes or anything happens, maintaining an assembly code and changing it at multiple places becomes really tough. So your question on the performance, we may leave something on the table, but that will require a super architecture expert of underlying architecture to probably get that from the chip, because we compare this hand authored assembly against which we compare our performance is authored by the architects of the particular DSP below. Those who designed that, who architected that DSP, they have written this assembly, and we are benchmarking against it. I hope this, like, I just anticipated the question and answered it, because this comes every time in Halide. Ravi, you can go ahead. Yeah.
Yeah. Okay. Can you see my screen still? Because something
Yes.
happened. So
Okay. Yes, Ravi.
Okay. Yeah, the performance is actually pretty much. We've been continuously working on the performance or the improvements in the performance. But yeah, it's not just about the raw performance as well. Like, it's also about the productivity. So one of the main goals of TVM is to improve the productivity of the engineers. So it takes very little time for a person who doesn't have any knowledge about the underlying hardware, or a person like who's familiar with machine learning operations, but doesn't want to bother about the underlying architecture. It takes very few hours for them to understand the programming model and write the code for any specific operation that they want to use. Okay, I have another example, but I just want to touch up on the schedule part and algorithm part. So this is the algorithm part where you actually write your main computation. Okay, and then you schedule it using different directives. I'll talk about them in the next slide. But this is what is the core of the operation. Like, it's the one part is algorithm and other part is schedule. So this is another example of average pool. So okay, so you still have the same compute part, which is the algorithm part here, which is doing the average pool operation, and then you have the schedule part here. These are the different directives like reorder and compute at, and some of the other directives that I'll show. So one thing that I want to highlight here is like your core.
Ravi, there is a question here.
Part of yeah.
From your code, I am guessing since TVM is close to C in representation, it should be able to exploit HVX similar to SIMD data packing. However, I don't see any parallel construct. Is multi-threading not supported?
Okay. This example, we don't have that. The multi-threading is supported. You can there is a directive called .parallel. It is supported. I mean, I'm specifically talking about TVM for Hexagon. So if the question is about multi-threading, that is supported. If the question is about like vectorization, even that is supported. That's obviously supported. We have dot vectorize construct, which actually generates the code for the vector unit for the SIMD operations. So this particular example is not covering all the directives. I will go to the next slide. So if the question is about this directive, which is vectorize, so if you use dot vectorize, similar to the ones that are here, the other directives, it generates the code for the vector unit. Okay, so these are some of the directives. There are other directives. We did not cover everything here. There's some examples, like you can use a split directive to split your inner loop and outer loop, and you can use tile for a sliding window tile. You can fuse multiple loops into single loop. So the basic intention here is to two parts. So one is to improve the efficiency of the computation using one vectorization, and the other is using your cache locality. Okay, so all these things are meant to be tried out so that you kind of get a better combination, or the combination that gives you a better performance. Okay, so for the in the programming model, once the algorithm is done, this part, the compute part is done, you can forget about it. Like it won't change. Okay, so only you keep changing the schedule part. You can experiment with only schedule part and try to get the better performance. And that's what Sahim was talking about when he talked about experience with the customers in China for box blur. So the entire operation, entire work there happened with changing the by experimenting different schedule directives. Okay, one other thing that I want to tell you here is like, so when you run this Python script, you are actually compiling it, which is not very, I would say, conventional in the sense like you're actually running the script, but the script, the execution of that script calls the compiler or invokes the compiler, parts of the compiler to generate the code. So the output of your script would be an assembly file or an object for a library that can be used on your particular target. So it basically cross compiles it to a specific target that you mentioned here. So in this case, we specified .hexagon, which is indicating that you compile this part of the code to hexagon and put that into a .o file or a .s file. I mean, you can save it in multiple formats, or you can create a shared object or a static library.
So there is a question here. You mentioned about offloading to GPU DSP processor. Is it achieved through a directive? Yes.
Yes, that's right. So the .hexagon is our directive to generate the code for hexagon.
There is another question. How TVM is different from MLIR framework in LLVM? MLIR to look similar to have ops which can be accelerator GPU specific.
Yeah. So MLIR, okay. At a very generic level, there are multiple areas of work that's happening now. TVM is one, and MLIR is another thing. Okay, so it's not at this point of time, it's not very clear like which is going to be adopted as, or which is going to become popular, which is going to be adopted as the standard one. Okay. Having said that, there are slight differences. I mean, TVM operates at a little higher level. I mean, it supports multiple frameworks, and it has its own IR, which is different from MLIR. But I think in future, when you hear from the TVM community or the TVM developers, so the way probably is going to be like, if MLIR becomes popular, there will be some translation between TVM's IR and MLIR, and it will be scaled to adapt to MLIR. Okay, but at this point of time, I mean, both of them are relatively new, so it's not very clear like which way it will go. But if in case ML becomes popular, like it will be like TVM will adapt to that. And
Yeah. So Samiran asked the question, which is better. So it's still time to answer. There is a question on split and tiling. Oh, recognize writing it there. The answer. So one thing is, the TVM, the two-way it is getting used. One is by the folks who want to do their machine learning part, but they are not worried about, or they don't want to understand the architecture part. For example, again, because TVM is new, I'll go back to the example of halide. There were material science engineers who needed to write image processing code to differentiate between plastic, rubber, human skin, sand, and all those things, which they could. They were material science engineers. They were not image processing engineers. They were not computer science engineers. They were material science engineers. So that's how like the TVM will enable people to do their machine learning without, irrespective of knowing the architecture and writing an optimized code for the underlying architecture. On the other hand, which we are like you will say then what is the other expectation? Other expectation is like, it is an open source work. A lot of systems guys here who are interested in systems. So you can contribute to TVM and making it backend efficient or more optimized for certain architectures, right, Ravi?
that's right, yeah.
And a lot of the split, tile, and all in detail will be covering in the next week's halide. Because of time, we distributed few things here and there. So TVM will actually enable, if you like, for example, the example why I took this, the non-efficient programmer. There are in industry, there are companies which are running a mobile company with 30, 40 employees. Not everyone is Samsung, Vivo, Oppo having a huge workforce. So that long tail in China, what happens is if we can provide them a framework like TVM, they will be able to write their ops. So TVM is more targeted to take machine learning at everywhere. Take machine learning, make machine learning or the deep learning available to everyone. Yeah.
Right. Just covered this one. I'll just go through this. So some of these things will be covered in detail. I mean, it's pretty similar to halide. So halide talk will cover some of these things with some examples. But even if you go through this, they're not very difficult to understand. So TVM use cases, I mean, these are use cases that we think about. We think how our customers would use it. Basically, the main use case is to provide ability to author and also there are a lot of machine learning models, frameworks that are changing very rapidly. We can't keep on extending something, or we cannot actually write a software that can support these things continuously. So we need to have some kind of tools for this thing and attempts to solve that problem. As we've been saying, like the hand coding ML ops or any kind of operations for a specific kind of hardware is pretty expensive. Not many companies or not many kind of teams afford that.
Yeah, there is a question, Ravi, here. Yeah, how does it plan? This we may not have the answer because we are focusing more on the edge compute or the handheld or the constrained devices side. But let me still read out the question. How does it plan to compete against cloud providers, for example, AutoML by Google Cloud and AutoML by Google Cloud, etc.
Okay. She mentioned like I mean we are targeting this for edge computing, which is basically doing it on your device, mainly the embedded devices. So
Yeah.
So these have completely different purposes, like they're not competing with.
Ravi, how much of your slides are remaining, Ravi? Because I want
I have
to. Yeah.
I have only one more slide.
Okay. Can I interject here? So one
Yes.
thing which I have requested a lot of researcher out here. So when we see a lot of research work, so the definition of computer in most of the research work is a high-end computers or x86s or the very, very powerful CPUs or the servers. But uh, we will request the community to focus their research also on the constrained CPU devices. The reason being is the more and more these handheld devices are increasing, and with the narrowband IoTs and the 5G low latency compute coming in, there are IoT devices which will be kept in Siberia, and the battery will be changed once in 10 years. So they have to be really efficient, really run on low energy, really do a lot of things on in lesser cycle possible. So those who are research scholars out here, when you are looking for your problem statement, I would request towards looking towards the constrained compute too, and not all the problem statements directed towards where the CPU is too powerful. Ravi, go ahead.
Right. Yeah. Yeah. That's an important point actually that I was talking about initially. Like the problems that we actually attempt to solve. Qualcomm or in general for the embedded systems, like we don't have a lot of computation power, and we actually have to work
On a battery.
on a battery and with limited memory. So we are constrained by a lot of things. So it would be actually very helpful to us if the research is if research attempts to solve some of these things, it's going to solve a lot of problems for us.
Yeah.
Okay. Yeah, I think pretty much done. I won't spend much time on this thing. So we have the tool sets, like LLDB is one thing that can be used to debug TVM issues, and we have the tools for profiling and analyzing the issues using traces. So that's it from my side. Thank you everyone for attending this and listening to me. Any questions, please feel free to ask me.
Thanks, Ravi. We have time for a few questions. Of course, we have been having questions. Aditya was the lead in that, but I'm sure there are other questions. Please feel free to ask either using the chat or you can unmute yourself and ask. Yeah.
Does TVM plan to support intermittent computing devices on the edge? Ravi, there is a question.
I don't understand like what is intermittent computing devices.
Yeah, what do you mean by intermittent computing devices, Aditya, here? Are you looking at like, the way some IoT devices which most of the time are in sleep but wake up time to time? Oh yeah, Ravi, intermittent devices are those which do not have constant power supply. The same Ravi IoT scenario was.
Right. Yeah.
Yeah, you have random bursts of power. You don't have the constant power. So Aditya, will it have battery or no battery? It has to have battery. Okay. So yeah, so we are the designers. So in that case, like your choice, our devices are with the battery. So we are doing a lot of IoT work, which is industrial IoT, which will be in the scenarios where the battery has to live for 10 years because the power is really bad. So uh, uh, there is a work going on internally on the energy efficient neural compute. So I'm not sure when it is on the timeline, but if it comes to for Qualcomm, I think Ravi, the choice will be TVM only. If you have to do a neural edge compute on a ultra low end devices.
That's right. Yeah.
Yeah. Any other questions, folks? Yeah, thanks, Aditya. You may come over next week in Halide. We may deep dive, and all the folks out here. Uh, there are a lot of things because we have to keep it. We have to keep the topic for general audience. We have to keep it at the generic level. But if you want to deep dive anything from the systems engineering perspective, feel free to reach out to us, and we will be able to answer 101 too.
All right, if there are no further questions, then we'll stop here. Thanks a lot, Ravi and Sushil, for supporting him through the answers. We'll have further sessions lined up next Monday onwards, and this session will formally close. Thanks a lot, Pratyush, for inaugurating the. I'll still call it inaugurating the session. And thanks everybody for joining. Thanks, Ashwina, for hosting the session. Bye, everyone.
Thank you.
Thank you.
Thanks, everyone.